P series. When I say P series, this is what I mean. Well, I mean the series, some n goes from 1 to infinity, of 1 over n to the p, for some fixed real number p. The question then is, for which p does the series converge? The claim is the following. This series converges if p is bigger than 1, and it diverges if p is less than or equal to 1. We can check this using Cauchy condensation. Well, let's just remember what Cauchy condensation says. It says to analyze the convergence of a given series, it's enough to look at the convergence of the condensed series. In this case, I'm trying to analyze the convergence of this p series. And here's the condensed series. How did I get this? Well, this is 2 to the n times the 2 to the nth term of the original series. Okay, so now all I've got to do is just determine whether this condensed series converges or diverges. How am I going to do that? Well, this series can be rewritten. This series is the same as just 1 over 2 to the n to the p minus 1 power, right? Look, I've got a 2 to the n in the numerator and a power of 2 to the n in the denominator. So I can rewrite that power in the denominator as just the p minus 1 power. Now this I could also rewrite. I could rewrite this as the sum n goes from 0 to infinity of 1 over 2 to the p minus 1 to the nth power. Why is this an improvement? Well, what kind of series is this, right? This series is just a geometric series with common ratio 1 over 2 to the p minus 1. And by condensation, if this series converges or diverges, so too does the original p series. So I've reduced the entire question down to just knowing whether or not this geometric series converges or diverges. And I know how to analyze that. If p is bigger than 1, then this common ratio is less than 1, and in that case, the series converges. And if p is less than or equal to 1, then this common ratio is bigger than or equal to 1, and in that case, the series diverges. If you've already seen integrals, you could also do this by using the integral test. So the integral test reduces the question about this series' convergence to the question about this integral. In this case, I'm trying to determine whether or not this series converges, and that happens if and only if the integral from 1 to infinity of 1 over x to the p dx has a finite value, if this integral converges. And this is true in this case because this function, f of x equals 1 over x to the p, is positive and decreasing on the interval that I care about. Okay, so all I've got to do now is just analyze this integral. And if this integral has a finite value, this series converges. And if this integral ends up being infinity, this series diverges. So let's see if I can compute this integral. So I'm trying to integrate from 1 to infinity 1 over x to the p dx. And by definition, this is the limit as n approaches infinity of the integral from 1 to big N of 1 over x to the p dx. And now, instead of writing 1 over x to the p, I could write x to the minus p. So this is the limit, n goes to infinity, the integral from 1 to big N of x to the minus p dx. Now I want to evaluate this, so I really want to assume that p isn't 1. Because I'm going to write down an antiderivative of this, and different things happen, right, if p is 1. But we've already handled the case where p is 1 anyhow. That's just the harmonic series. Okay, so let's keep going. Assuming that p is not 1, then I can evaluate this definite integral by finding an antiderivative of x to the minus p, right, via the fundamental theorem of calculus. So this is the limit, n goes to infinity. What's an antiderivative of x to the minus p? X to the minus p plus 1 over minus p plus 1. All right. Add 1 to that exponent, and I divide by that same quantity. And I'm evaluating this from 1 to n. So now I just got to plug in n and plug in 1 and take the difference. So this is the limit, big N goes to infinity, of n to the minus p plus 1 over minus p plus 1, minus what I get when I plug in 1, which is 1 over minus p plus 1. I could combine these two fractions. This is the limit, n goes to infinity, of n to the minus p plus 1 minus 1 over minus p plus 1. Okay, now the whole story is being told by this limit. If this limit has a finite value, then so does this integral, and that means that this series converges. So how do I check that? Well, the story is really being told by this power here, right? N to the minus p plus 1. What happens? So if minus p plus 1 is positive, then n to a positive power, this is going to be very large, and, well, this limit then will be infinity. That means that the series will diverge. So then the series diverges. If, on the other hand, minus p plus 1 is negative, then I'm taking a big number, but I'm raising it to a negative power. It's going to be ending up close to 0. And in that case, this integral will have a finite value, and that means that this series converges. So then converges. And maybe it's a little bit complicated to think about what these two conditions are. Instead of saying minus p plus 1 is positive, I could instead just say p is less than 1. And instead of saying minus p plus 1 is negative, I could just say that p is bigger than 1. So now we've shown the whole story, right? If p is less than 1 or equal to 1, the series diverges. And if p is greater than 1, then the p series converges. Even when the p series converges, the actual values that we're getting can be quite mysterious. For example, the sum of 1 over n squared, n goes from 1 to infinity, is pi squared over 6. The sum of the reciprocals of the fourth powers, the sum of 1 over n to the fourth, n goes from 1 to infinity, is pi to the fourth over 90. The sum of the reciprocals of the sixth powers, the sum n goes from 1 to infinity of 1 over n to the 6, is pi to the 6 over 945. So this is 2, 4, 6. What about odd numbers, right? What's the sum of 1 over n cubed? N goes from 1 to infinity. Well, hundreds of years ago, Euler calculated an approximation, right? He calculated some of the decimal digits of this number. And then not so long ago, Apéry in 1978 showed that this was an irrational number. But as far as we know, it's not a rational multiple of pi cubed. I think that story is pretty cool, right? I mean, in the 1730s, Euler approximates some number, and over 200 years later, Apéry comes along and says that number that you were approximating is irrational. I mean, to be doing mathematics means that you're part of a community that will outlive you, right? You're joining into a conversation with people from hundreds of years ago.